In this video, I want to continue along our path of trying to figure out how to calculate the determinant of any square matrix that we're given. Before we get to the most general way of doing this, that is to situations where we have any matrix and we want to be able to calculate its determinant, I want to look at specific examples where we can calculate the determinant pretty quickly. It turns out that in general, to calculate a determinant requires some work, either by hand or using software and thinking about how much time the computer takes. It's a complex calculation. In this video, I'm going to look at situations where it's not so bad. So we still won't know how to calculate any determinant, but this is important because given that it's a bit of a complicated calculation, you don't want to do a full-on calculation if there's some quick reason that you can immediately know what the determinant is. All right, so before we do dive into the video, I wanted to introduce some notation. If we're talking about the determinant of a matrix, there's two main ways to write it. We either just do det parentheses the matrix, or we could put vertical bars on either side of the matrix. And I'll show you how that looks when we actually write out matrices. I tend to think that this notation is better. It's clearer. It's harder to misunderstand what it's saying. This notation is not really that great, but it's really common. And the problem with this notation is, as we'll see, it's easy to miss that it's even there. Okay, so this is our notation that we're going to use. And the first matrix that I want to point out that I don't think I've said this yet, but that we definitely know the determinant of is the identity matrix. Now, pause the video if you want. Think for a second. What is the determinant of the identity matrix? Well, the determinant of the identity matrix is 1, because the identity matrix doesn't do anything to space. It just leaves it where it is. And so all n volumes are left exactly the same, or in other words, they're scaled by 1. I could write this in a few ways, right? I could write det of I equals 1. And when I was talking about these vertical lines, this would be a common way to write it if we're in R3, right? To say that the determinant of the 3 by 3 identity is 1. And this is where we start to have issues with this notation. This right here, it would be really easy just to glance at and not realize that it was a determinant sign, right? You might just kind of implicitly think that you have little brackets here. And so I think this notation is to be avoided unless it's really clear what's going on, right? If we're in the middle of a determinant calculation and you write this, fine. But if you just all of a sudden out of nowhere want to take the determinant of a matrix, I think this is better notation because no one is going to misunderstand what you're saying. And the whole point of notation is to be clear. Okay, so we have the determinant of the identity matrix. We know that. We also know the determinants of elementary matrices. So to remind you about that, we have these 3-row operations that have corresponding elementary matrices, and we know what their determinants are. When we multiply a row by a constant, the determinant is just that constant. When we switch 2 rows, the determinant is -1. And when we add a multiple of 1 row to another row, the determinant is 1. We have to be careful here. If we try to do more than one thing, we don't have an elementary matrix, and what I just said is not true. So if you're going to switch around a bunch of rows at the same time, not just 2, you no longer know that the determinant is -1. It could be +1, right? Because maybe you've switched, maybe you've kind of reflected twice, right? So be really careful with that. All right, so we have determinant of identity, determinant of elementary matrices, and then there's a bunch of properties that we've mostly talked about that can allow us to do calculations a little faster. So for one, we know that the determinant is multiplicative. And so if we're working with a product of 2 square matrices and we know the determinant of each individual matrix, we don't need to recalculate the determinant of the product. We know that it's just the product of the determinants. A corollary of this, along with the fact that the identity has determinant 1, is that the determinant of the inverse of a matrix is 1 over the determinant of a matrix. We'll actually see this really soon, that we're going to be in a situation where we know a matrix, we want the determinant of its inverse, but we actually don't necessarily care about knowing exactly what the inverse is. And so we can save ourselves a lot of time. Rather than calculating the inverse of the matrix and then calculating the determinant, we can just calculate the determinant of the original matrix and divide 1 by it. And then the final property is that if our matrix isn't invertible, the determinant is 0 if it squishes space. And so, for instance, if your matrix has a row or column of zeros, the determinant is 0. If your matrix has duplicate rows or duplicate columns, it's not invertible, the determinant is 0. So if for whatever reason you know that your matrix is not invertible, you don't need to calculate its determinant. The determinant is 0. Okay, so these are the easiest ones. That is, if somehow you can apply any of these things, you can really quickly calculate the determinant. And then for small matrices, the determinant is not so bad. So this is where we're really getting into formulas. Let's look at, we often skip n equals 1, but why not? So for n equals 1, the determinant of the matrix A is just A, right? It's just the individual entry. For n equals 2, the 3 blue 1 brown video both presents this formula and gives a nice explanation visually in terms of parallelograms for why it's true. So I recommend going back to that determinants video if you want to see why this is true. But the determinant of the matrix A, B, C, D is AD minus BC. And in that video, they show how the parallelogram that this linear transformation takes the unit square to has this area, or maybe this thing is negative, and that means that the transformation has changed the orientation of the vectors. And so we can quickly apply, I'm not going to do an example for n equals 1, but we could quickly apply this. If we wanted the determinant of 2, 5 minus 1, 3, this is 2 times 3 minus 5 times negative 1, and our determinant is 11. I'll point out this formula showed up before. It actually showed up in the formula for taking the inverse of a 2 by 2 matrix. And remember, we're in that formula, we divide by this number, and what I said was that this is a little scarier. It should be. Anytime you're dividing by something that might be 0, you should be worried. But if this were 0, that would mean that the matrix wasn't invertible. And so the fact that we're dividing by 0 is fine, because we're trying to find something that doesn't exist, right? If you have a non-invertible matrix, it doesn't have an inverse. And you start doing this and you say, oh, this doesn't look too bad, right? N equals 1, we have 1 term in our formula for determinant. N equals 2, we have 2 terms. And this is far too few examples to notice a pattern, right? But we might hope that, oh, when we get to n equals 3, maybe we just have to do kind of 3 things, and we'll get a nice formula for the determinant, but we don't. That's not how it works. So n equals 3, there is a formula, and I'm going to write it out, and bear with me here. Now, this is a big enough matrix that we should be smarter about how we label things, right? Using letters for each, or using a new letter for each entry is not a good idea. So we're going to use indices. So this is just an arbitrary 3 by 3 matrix, and I'm taking the determinant, and there's a formula here, and I'll write it all out, and then I'll talk about what it is. And if you haven't seen this before, try to see if you can figure out any sort of pattern to what I'm writing down. I'll give you a hint. The negative signs are really hard to figure out, why things are positive or negative, but just how I'm choosing to combine entries. Why am I choosing A13 and A21 and A32? So this is the determinant of this 3 by 3 matrix. So our pattern, unfortunately, didn't hold, right? 1, 2, 6. And if that if those first three numbers jump out at you as the factorials, right? 1 factorial, 2 factorial, 3 factorial, you're right. So it turns out that the number of terms in the formula for the determinant of an n by n matrix is n factorial. And n factorial is huge, right? 5 factorial is 120. And so even this n equals 3 formula is totally unreasonable to use. So I wrote this down, but like, let's be clear. Do not use. This is not how we're going to find the determinant of a 3 by 3 matrix. We're not going to memorize exactly what this formula is. It's unreasonable. N equals 4, there's already 24 terms. And even n equals 3, this is too much. But I want to take this and give you a sense for what the general formula is. If as I was writing, you were trying to follow what these terms are, 1, 1, 2, 2, and 3, 3, that's these three entries. 1, 1, 3, 2, and 2, 3, that's these three entries. Let's just choose some other one. 1, 2, or actually, let's do a more interesting one. 1, 3, 2, 1, and 3, 2. That's these three entries. I'm picking three entries from the matrix so that they don't fall in the same row or column. So I'm picking exactly one entry from each row and each column. There are 6 ways to do that, because I have 3 choices for what I choose from the top row. And then once I've chosen one, in the second row, I have to choose something in a different column. So I have 2 choices. And then I have 1 choice at the bottom. And more generally speaking, and I've thought a lot for what's the best way to write this formula out, because I'm not going to write out the whole formula. This is going to be my best attempt at giving you a sense for what the formula looks like without writing it out. What I'm going to do is I'm going to add up a bunch of things. So this sigma is a sum, right? And what I'm doing is I'm going to pick an entry from each row and column. So I'm summing over all ways to pick exactly one entry from each row and column. So I have all these different ways I can pick one entry from each row and column. I have n factorial ways, right? I have n choices in the first row, and then I only have n minus 1 in the second row, and so forth. And what I'm going to do is I'm going to multiply all the entries. And there's either not going to be a negative sign or there is. So I'll write this like this. Maybe times -1. And I think this is a good way to write out the formula because it doesn't allow you to use it. We'll see there is a way to kind of use this formula, but it doesn't allow you to use it. But it does kind of allow you to understand what it's telling you. It's saying that there's actually a formula for the determinant, and the way we do it is we figure out all the different ways to pick exactly one entry from each row and each column. We multiply them together, but maybe we have to multiply by a -1. And that's what's going on right here. And it turns out even if you don't really know when to multiply by a -1, this is still useful. And we'll see how that works. Okay. So let's look at, I've claimed that this is useful without giving you any sense. So I want to give you an example where this is useful. I want to calculate the determinant of the following matrix. The 4x4 matrix. And all we know is that the formula for the determinant of a matrix is always to pick exactly one entry from each row and column. We multiply the entries, and maybe we multiply by -1. And I've given you enough information to figure out that this determinant is either -15 or 15. And I'll tell you which it is. But let's see what I mean. As you start picking entries from each row and column, you realize that unless you're really careful, you're going to end up picking a zero. And if you pick a zero and multiply a bunch of things together, you're going to get zero. And in particular, the only entry that I can choose in the first column is 2 without getting a zero. And once I've chosen the 2, I'm no longer allowed to pick another entry from the first row. And then when I go to the second column, the only entry I can choose without picking a 0 is 5. And similarly, I realized that the only way to choose an entry from each row and each column without having a 0 is just by picking the diagonal entries. And so I get that this determinant is 2 times 5 times 1/2 times -3, but I don't know if it's multiplied by -1 because the formula didn't tell me, right? This kind of, I don't know, vague way I've written it. Now, it turns out that when you pick your entries from the diagonal, you don't multiply by -1. And so actually, this determinant is -15. And I want to generalize this, but hopefully you can already see that understanding what the formula for the determinant looks like is actually kind of useful in this example. We quickly narrowed it down to only a few choices, and you can convince yourself if you think about what this would look like as the product of elementary matrices that at no point do you need to switch a row and column. So in any case, we have this kind of nice approximate calculation that gets us almost all the way to the answer. So this is our next example. There you can maybe see that this is not a coincidence. The fact that we had all these zeros below the diagonal made a difference. This is what's known as a triangular matrix. So a triangular matrix, there's kind of two types. I've given you what's known as an upper triangular matrix. An upper triangular matrix, all entries below the diagonal are 0. Right, so the diagonal is these entries, and everything below the diagonal is 0. And you could similarly imagine that a lower triangular matrix, we would apply the same logic to. So in a lower triangular matrix, all entries above the diagonal would be 0. So that's not the case here, but that's referring to these entries, all the entries above the diagonal. So when we have a triangular matrix, the determinant is just the product of the diagonal entries. So the determinant of a triangular matrix is the product of the diagonal entries. We don't need to go through some complicated process. We just multiply them. So now that we know that, when we get to this matrix, we just multiply the diagonal entries. We know that we don't have to multiply by a -1. We get our determinant. I want to recap what we have. What matrices do we know how to take determinants of? So we know the determinant of the identity. We know the determinant of elementary matrices. We have some properties that can make things a little bit easier for us, and in particular, if we know a matrix isn't invertible, its determinant is 0. For n equals 1 and n equals 2, we have nice formulas for the determinant. And then if we have a triangular matrix, we can quickly calculate the determinant by multiplying the diagonal entries. That still leaves a lot of things that we don't know how to take determinants of. And I'm not going to explain how to do that in this video. Those are for separate videos, but I want to just give you kind of looking forward. There'll be 3 main ways to find determinants of arbitrary matrices. That is, you're given any square matrix and you can find its determinant. And one of them is what I've alluded to a bunch, row operations. We know the determinants of elementary matrices, and we can figure out how to write a matrix as a product of elementary matrices and figure out its determinant. The second one we'll talk about is what's known as cofactor expansion. And what cofactor expansion is going to be is it's going to be a nice way of applying this formula. Basically, rather than thinking of this as, we'll use the fact that this formula exists, and rather than thinking of it as one single formula, we'll go through a series of steps that basically reproduces this formula and also keeps track of whether you need a -1. So we'll see that in a future video. So this is to say this formula is actually going to be useful. This idea of cofactor expansion will apply this formula in a more organized way. And then finally, and this is obvious once it's written down, we have computers, right? So determinants are complicated enough that it's actually very common and often the right choice just to enter your matrix into software and have the software calculate the determinant. So that's what we'll look at going forward.